So acids and bases, we'll start off with some nice simple definition type ones. Nitrogen 4 oxide, that's NO2, reacts with water, here's the equation, to give HNO2 and HNO3. Nitrous and nitric acid, however, the A-level is using the terms that nobody else uses, nitric 3 acid for the nitrous and nitric 5 acid for the nitric, defined as being acids. Define an acid, now at this point in the A-level, an acid is a H+, poorly known as a proton, but that's what everyone says, so we'll call it that, H+ donor. Write an equation to show nitrous or nitric 3 acid behaving as an acid. Well, that's that one there, HNO2. So HNO2 will react with water. It's an acid, so we'll make H3O+, leaving behind NO2-, the conjugate base. And because this is a weak acid, we'll put in the reversible arrows there to indicate that it reaches equilibrium. It doesn't completely do its acid thing. When concentrated nitric 5 acid mixed with conc sulfuric acid, the reaction shown below occurs. This is the reaction that's associated with the nitration of aromatic compounds, if you've got that far yet. Right now, we don't care about aromatic compounds. We just need to explain it in terms of acid-base behavior. So let's look at what we have here. The sulfuric acid, H2SO4, obviously becomes the HSO4-, so it loses an H+, which means it's going to be acting as an acid. Both of these are strong acids, but H2SO4 is a stronger acid. Now, if H2SO4 is losing H+, it's losing it to something, thus something else is gaining it, and that something else that gains is very obviously the HNO3 to become H2, see the 2 there, H instead of 1, NO3+, so therefore the nitric acid is behaving as a base, because in this case, because it's with a stronger acid, it will be forced to do what it really doesn't want to do, and that is to gain, to accept an H+, to make its conjugate acid. Okay, so HNO3 is a base, making its conjugate acid. That is something you rarely see, except when talking about nitration of aromatics, and then the sulfuric acid acting as a acid, leaving behind its conjugate base. Little bit of geology here. Hydromagnesite is a mixture of magnesium carbonate and soluble impurities, one assumes soluble in water. A student crushed some hydromagnesite, added a sample of mass 0.889 grams to excess dilute hydrochloric acid, which would react therefore with the magnesium carbonate component. A, explain why the rock was crushed before being added to the acid. Nothing acidically specific about this. Anytime you have a solid with which you wish to do a reaction, you want to crush it so that you increase the surface area, so it's powder instead of lumps and stuff, because the more surface area there is, the more of the solid is available for reaction. Thus, the rate of reaction will be increased. And the equation for the reaction between magnesium carbonate, dilute hydrochloric acid. Well, the magnesium is a spectator ion. We can think about it as just doing a metathesis reaction. So the magnesium, which is 2+, grabs itself 2 chlorides. Both of these in this case will be spectator ions, leaving 2 H+ to go with the carbonate, thus making H2CO3 or carbonic acid. I put that in quotes because that doesn't hang around for very long. It decomposes into carbon dioxide and water. So the whole reaction, MgCO3 plus 2HCl, goes to MgCl2 plus CO2 plus H2O. Just like I said. Ammonium salts, very important chemicals, is used in nitrogen source in fertilizers. When cold, aqueous sodium hydroxide is added to an ammonium salt, the following equilibrium exists. So there's your ammonium reacting with the OH-, reversibly going to NH3 plus H2O. Identify the two acid-base conjugate pairs in the equilibrium. Well, conjugate pairs are two substances that differ by H+. So if we start with NH4 plus and we match it up, there's an N, there's 3 hydrogens, so the difference between them is NH4 plus has lost an H+ to go to NH3, thus remaining behind the OH- is going to be gaining an H+ to become H2O, but again differs by H+. If we assign which is the acid, which is the base, they differ by H+. The acid of the pair has it, because when it acts as an acid, it gets rid of the H+, it donates the H+, leaving behind its conjugate base. Thus NH4+ and NH3, the NH4+ is the acid, NH3 is the base, and now OH minus H2O, the OH minus doesn't have it, the H2O does have the H+. Right, expression for the ionic product of water, Kw. Well, you have two waters, that one of which acts as an acid, the other one of which acts as a base, thus making the conjugate acid of water, H3O+, and the conjugate base of water, OH-. So that's the equilibrium going on. So the equilibrium constant will be, of course, the righties, H3O+ times OH-. Do note we're talking about equilibrium, divided, of course, by the lefties, but by convention, because the lefties are H2O liquid, we leave it out. So Kw, concentration H3O+ at equilibrium, times the concentration of OH- at equilibrium. And remember, this is an equilibrium that exists, and thus an equilibrium constant that describes the existence in every aqueous solution. An alternative way you can write it, if you want to, is you can just, instead of thinking of it as a water reacting with the water, just a water dissociating to give you the H+ and the OH-. Kw is the H+ times the OH-. And remember, in water, H3O+ aqueous and H+ aqueous are interchangeable depending on whether you have the water as a reactant or not. So come to our first calculation. Ethanoic acid is a weak acid with Ka 1.78 times 10 to the minus 5. Calculate the pH of an aqueous solution of ethanoic acid with a concentration of 0.22 moles per cubic decimeter. Now I'm going to vary from the standard A-level approach here because I see 0 point in memorizing particular equations to use at certain points and certain types of calculation when they don't work for every example of that type of calculation. I would far rather just say, hey, a weak acid is just a substance in water that is reaching equilibrium. So let's just treat it as a regular equilibrium problem. And that's the equilibrium constant. The fact that it's a Ka doesn't affect the fact that it is an equilibrium constant. So here is our reaction. There's the ethanoic acid plus water, going H3O plus the acetate, or the ethanoate, the conjugate base. There's the Ka expression. We know Ka. We would like to have the pH, so that's effectively the equilibrium H3O plus concentration. To get that, we would also need the ethanoate concentration at equilibrium and the ethanoic acid concentration at equilibrium. So because we want one of these, we don't know the other two, we set up a SCA chart. So let's be sure we see where we're going from. Ethanoic acid starts at 0.220, so our assumption is that's all we've got in the solution at the start, no H3O plus, no ethanoate. More complex type situations would say, well, actually, seeing as how you're starting off with water, you've already got 1 times 10 to the minus 7 of the H3O plus. Ordinarily, that is so small that we don't worry about it. Change line, as usual, XXX. All the coefficients are 1, 1, and 1, and 1. So bring down the minus X for the reactants, positives for the products. Put them together, and there's the equilibrium concentrations, 0.220 minus X, X, and X. So the problem has shifted from find the H3O plus concentration to find X. Obviously, you can see in this case it's the same thing, but the nice thing again about these charts is that they relate all of those equilibrium values to one variable, X. Pop all that into our nice little equilibrium constant expression. We know the Ka, and then the concentrations from the SCA chart, X times X over 0.220 minus X. Now we say this is a pretty small number. If this is a small number, that means that at equilibrium there won't be very many products. If there aren't very many products, X is small, and maybe X is small enough that we can ignore it compared to 0.220 and say that 0.220 minus X is about 0.220. Now let's solve that problem, because 0.220 is a lot nicer than 0.220 minus X. We get that X is 1.98 times 10 to the minus 3. Now at this point we should check our assumption. So the way that I like to check it, and there's several ways to do it, but this is the one I think that works the most consistently, is we just say, what was our error in ignoring x? Well, the way you do that then is you take the value of x that you've said is small, you divide it by the number that you've said is big by comparison, multiply by 100, and that effectively gives you the percent error associated with this assumption. As long as it's less than 5%, we're going to be okay. So we can go back here and say x is 1.98 times 10 to the minus 3. That means that the concentration of H plus or H3O plus, which is x, is 1.98 times 10 to the minus 3. Now we want the pH, so that's minus the log of that, which is 2.70. Okay, there will be those people who say you'd have got that if you just multiplied the concentration times the Ka and square rooted. That's indeed what we did here, but I would prefer that you think your way conceptually through what we're doing rather than just using blindly some equation. When a solution containing the weak base ammonia is neutralized using the strong acid sulfuric acid, a solution of ammonium sulfate is formed. Suggest the pH for this solution, given a reason for your answer. So ammonium sulfate, NH4 twice, SO4. That, of course, is a soluble ionic compound, which means in water it exists as its dissociated ions, so 2NH4 plus and SO4, 2 minus. Now, SO4, 2 minus is a very, very weak base. Okay, it's an anion, so it's going to be a base, but it's an extremely weak one because its conjugate acid, HSO4 minus, is a very good weak acid. So sulfate is a very weak base. Conversely, NH4 plus, quite happy acting as an acid to react with water to give us H3O plus and NH3. And so the solution here will be acidic. So a very weak base and a weak acid. The weak acid is going to dominate over the very, very weak base. pH, I say, will be about 2 to 6.5, depending upon, first of all, the concentration, and then, of course, just how good an acid is NH4+. Now, at this point, I would say NH3 is actually a pretty good weak base, as weak bases go, which means that NH4+ is going to be a pretty bad weak acid, not nearly as weak as sulfate is a base, but because NH4 is a pretty bad weak acid, that means the pH will probably be between 4 and 5.5 rather than this range up here. Okay, now different teachers will teach you different assumptions to make in terms of the pH, but this I would hope would garner you full points from the A-level board. Now, whether you garner full marks for this question, if you do it correctly, depends upon how alert and astute the marker is. Sulfuric acid, hydrochloric acid are strong acids. Can't quibble with that. Calculate the pH of a solution 0.010 moles per cubic decimeter sulfuric acid H2SO4. Now, according to the A-level, you've got 2 protons in here, and the A-level assumes both of these are strong. So that means that when you dump 0.01 molar H2SO4 in water, you're going to get twice as many H pluses. So the concentration of H plus 2 times 0.01, which is 0.02 molar. So thus the pH is minus the log of that, which is 1.7. However, that's not the correct assumption. Certainly the first proton in sulfuric acid is strong. So you get sulfuric acid, H2SO4 plus water, giving you H3O plus HSO4 minus. HSO4 minus is an acid, but it is a weak acid. Okay, so the HSO4 minus doesn't have a huge big Ka. It's got a Ka of 0.01. Now, it's not disgustingly small, but it's still not a strong acid. So what we have to do is we have to take the first dissociation as read, but now investigate more closely how the HSO4 minus behaves. Reacts with water, reversibly giving some more H3O plus SO4 2 minus. There is the Ka value. We know the Ka, but we actually want the H3O plus at equilibrium. To get that, we need to know the sulfate at equilibrium and the HSO4 minus at equilibrium. So we set up a SCA-chart. Now look at how I've done this. At the start, I've said we've got 0.01 HSO4 minus because all of the H2SO4 that I started with gave me some HSO4 minus. That also gave me H3O+. So the concentration at the start for this equilibrium is 0.01 HO4- and 0.01 H3O+. Really important that you first of all appreciate that this first equation, no problem with that at all, it goes to completion. So 0.01 sulfuric acid gives us 0.01 of this, 0.01 of that. Change line as usual, minus x, x, and x, equilibrium, 0.01 minus x, 0.01 plus x. And x, pop that in to the expression together with the fact that Ka is 0.01, and we get this. Now at this point, there is no way that we can say that x is small. Okay, we can't eliminate x at all because this is not a terribly teeny Ka like in the last one, which means we have to solve a quadratic equation. Okay, so first of all, multiply it all out. So 0.01 times 0.01 minus x, and then on top 0.01 plus x times x. This is what you get when you multiply it all out. Check it for yourself. Pop into x is minus b plus or minus square root of b squared minus 4ac all over 2a. The b is 0.02, so that's minus 0.02. That's b squared 0.02 minus 4 times 1 for the a times minus 1 times 10 to the minus 4 for the c. Do that and we get x is 4.14 times 10 to the minus 3 molar. Okay, now at this point, there are those who would say, whoa, that was fun, wasn't it? Let me take minus the log of that. You can't do that. You always have to go back and refer to the SCA chart. The H3O plus concentration, or H plus concentration, is the 0.01 that was there at the start, plus the 0.004, which is this 0.00414. And the pH is 1.85. So you can see that by taking into account correctly what happens to the HSO4-, you actually get a pretty significant difference between the pHs. Remember, this isn't just a difference of 0.15 because pH is a logarithmic scale. Okay, so the H plus according to the Silly's assumption, 0.02. The H plus according to the correct one is 0.014. So a significant difference between 0.02 and 0.014. Anyway, I'm sure that every A-level exam, wherever puts this on, will be wanting you to do the flawed assumption rather than the full calculation. But I do want you always to be aware where A-level is either wrong or oversimplifies things.